Hello students, welcome to another tutorial on static equilibrium. In this video, we're going to look at this interesting question. We're going to try to find the tension in the rope that is tied to a suspended beam pivoted at the bottom. Now, before we get to this question, let's start with the task I left you guys with in the previous video. So if you haven't seen that video, I'll leave a link in the description. I'm going to cruise through the steps that you need to use to work out this problem, since most of the methods that you use are similar to the ones which were used in that video. So in this video, we're trying to find the frictional force exerted on block A, given the mass of that block and the mass of block B, and then also the coefficient of friction between block A and the surface was given. So now that's the key thing that I wanted to highlight, that brought me back to this question, because of the responses I was getting. So let's quickly go through the procedure that you have to do to work out this question. So first and foremost, to find, we're going to start with this side. What we want to find, let's label this as T1, this as T2, and then you can say this is T3. So just as we did in the previous question. So the first thing that we want to find is, what this T1 is, and then later we're going to come back to this side. Now I'm going to explain towards the end why it is important to do this in this case. So when we get to get T2, all we have to look at is the mass of B times the weight. So if we sum the forces in the Y at this point, we see that they should add up to 0 if it is to be in equilibrium. So this means that T2 going up minus MBG going down must be equal to 0. So this gives T2 the mass of B, which is 2.25 times 9.8. This will give us 22.1 newtons. So from here, we can easily work out this part, what happens here, and this will give us T1 also to be equal to 22.1 newtons. So if you want to see how this comes up, how T1 gets to be 22.1 newtons, the mathematics on how we use this to come to this junction and to work out what is happening here, this was all done in the previous video. So again, I'll leave a link in the description so you guys can easily, if you're not sure, or maybe you didn't see that video, you easily find it. But T1 comes out as 22.1. Now the next part would be to find the friction that is acting on this object going backwards, provided the system is to be in equilibrium. Now this is where I wanted to emphasize. So what you have is a system like this, and then on the surface you have there's some friction. Now I want you guys to get one thing. What you have is mg going down, the weight, and then going up you have the normal. So you can easily get frictional force by multiplying the coefficient of friction times the normal. Let's just write it up to n. So in this case, for a level surface, this comes out as mu mg. So this, in this case, is going to end up as the coefficient 0.32 by the mass, which is given as 8.5 times 9.8. Now, if you multiply this, you get your force of friction as 26.7 newtons. Now, this is why it gets tricky. Most students were giving me this as the final answer. But then look at one thing. Let's try to look at this. Let's include these forces and try to think about it. If you say force of friction is to this side, we all agree, first of all, that it's going to the left. So, and it has a value of 26.7 newtons. And then the force it is opposing is T1, and we've seen that T1 is 22.1. Now then the question is, if you add the forces in the x-axis, Do they equate to 0? Of course not, because 26.7 is greater than 22.1. So according to this setup, it is showing that this system is supposed to move to the left, which is not true, because this system is not supposed to move at all. Force of friction is just opposing the 22.1. Now, what do I mean? Well, the force of friction we find here, it's not necessarily the friction that is acting on the body, but instead, it is the maximum friction that this object can exhibit. What does that mean? Well, look at it like this. If you were to plot friction against the force exerted on a body, let's say this side, what you have is the force exerted. Let's say T1, and even say this is T1. But this is just generally for forces. And then what you have on the y-axis, let's say here you have the friction the body will experience. So if you exert a force of, let's say, 2 newtons, because friction has to oppose this force, friction will also get the same value of 2 newtons. If you change the T1 now to be, let's say, 5 newtons, force of friction will also change to 5 newtons. Take the applied force to, let's say, 20 newtons. Of course, this don't take the spaces to be to scale. Frictional force will also get 20 newtons. So I hope you're seeing what is happening. The force of friction is always proportional to the force applied. Okay, let's take this a little bit more. So the force of friction is proportional to the force applied. Now, there is a limit to what values friction can take, and that's the value that we found. In this case, the limit for friction is 26.7. So this is the limit. Friction cannot exceed this 26.7. So if you extended the force applied to 26.7, friction will match that. So what you have is a linear relationship. Increase the friction, increase the force applied, friction will match it. So that throughout, the system maintains equilibrium. But if you exceeded the force applied, let's say the force applied now becomes greater than this 26.7. Let's say now you apply 30 newtons. Well, friction cannot match this because we have now reached the maximum friction possible for this object. So friction will not be able to match this. And because it won't be able to match this, then you have an imbalance. And eventually the object now moves towards that imbalance. Now, of course, the behavior will not just be something like this. It tends to reduce a little bit before it then normalizes to be uniform. It drops a little bit. But the key thing I wanted to highlight is the behavior just until when you reach the maximum value. This is what I wanted you guys to get. So if the applied force is less than the maximum, the friction the object will experience will be equivalent to the applied force. So if you apply 20 newtons, the frictional force, 20 newtons. Applying anything less, the friction experienced exactly that. You only have differences when you exceed the maximum friction the object can experience. So in this case, the question was to find the frictional force the body experiences. What we found is the frictional force max, the maximum frictional force, 26.7. But the applied force, T1, was 22.1. So in this case, try to think about it. Try to decide. Having heard the explanation this time, what is going to be the frictional force that this object will experience? Not the maximum, but the one that it will actually experience if it is to remain in equilibrium. So I hope you guys were able to figure it out now, because the frictional force it is going to experience is going to be equivalent to T1, which is 22.1 newtons. Now, the second part of the question was saying, well, what if we double the mass? So if you double the mass to twice m, notice that you have not changed what T1 is. So does the force of friction change as well? So try to think it through. Having gone through the explanation, try to answer it. You can pause the video if you have to. Okay. Now I hope you're able to figure it out. And then for those who just want uh, to come for the ride, let's just go through it. So you haven't changed what T1 is, as I pointed out. The only thing you've done is double the mass. Doubling the mass just changes the maximum friction, because the maximum friction is mu mg. So now it's 2 mg. So you've just doubled the maximum friction. But since T1 has maintained the value, and what we know is that the two are supposed to be equivalent for as long as T1 has not exceeded the maximum. In this case, clearly, T1 is not going to exceed the maximum. So in other words, the force of friction will remain the same, equivalent to T1, which is 22.1. The only thing doubling the mass has done in this case is to double the maximum friction this object can exhibit. So I hope that's clear. Let's quickly move on to the aim of this tutorial. I'm going to, since most of the methods we're going to use here, the methods that we've seen already, so we'll try to just cruise through this one. Okay, so we have a few scenarios here. Let me just sketch it. So we have something like this, and then we're saying it is fixed somewhere here. We have a number of forces that are acting to this point. And then apart from that, we have tied this object at some point somewhere here. Now, the L/4 there is just an error. So from the question, the key thing that we're supposed to get is this point, starting from this point, it is at a length 3/4 of the whole. And then we have a weight, the weight of this object acting to this point. Let me use blue for these colors, for these forces. And then the weight here is going downwards. And the position, of course, since this is the weight, it's halfway. So it's 1/2L or L/2. Now at the far end as well, we have a mass. And this mass has a weight of 2000 newtons. Okay, so of course, the weight of this object becomes the tension in this string. So I've just gone ahead to just draw it as a force. Okay, now what they want us to find is in the first case, we have to find the tension through this rope. So we can label this as T, since that's our tension. That's what we want to find. The weight of the object can be calculated, the weight of the beam. Okay, it's given as 400 newtons. So this is 400 newtons. So as we saw in the previous case, there are a number of ways we can work it out, but the easiest way to work this one out is just the method that we can use in this case is just to use the dimension of this beam as the distance and fix it to the way it is. So this is going to be our x-axis. Our y-axis will be the perpendicular ones. So we're going to get the components of each force that are perpendicular to this distance. So in this case, it's going to be this one. And then for this force, it's going to be, so all we need is perpendicular. So this is perpendicular. So this is the component that is going to be perpendicular. And then for the tension that we're interested in, perpendicular is going to look like that. So again, the rest of this is now just resolving vectors. So the next step is identifying the angles. What are the angles that we have to work with? The question does give us this angle. This angle is given as 50. So of course, you guys shouldn't have trouble remembering that then this angle here is also 50. And this angle here is also 50. Now the next part would be what angle are we going to use to get this component? So for that, since we should tell that if this is a horizontal rope, then this is going to be 90 here. So we kind of are interested in this angle, or we can say that this 50 is equivalent to this 50 here. And if this is 50 and we know this is right angles, so if this is 50, then this must be 40 as well. Or we can still use this 50 here. So this is 50, this here is 40. So I hope you guys are able to follow. That. Now the next thing is, we're going to we can stick to the 50. We can use the 50. So next thing is, let's resolve the forces. So I'm going to work out this one here, and then you guys should be able to work out the rest. But then again, if you're still struggling with converting vectors, resolving them, just to check out my series. Okay, so if I was just to sketch that force, the T force, so what you have is this, and then the force is in this direction. And then the angle given is 50 here, the angle we want to work with in this case. So the component we're interested in, the component we want to find is this one here, the one that is at right angles to the base. So we notice that if this is T, this is opposite, so the ratio is sine. So this is going to be T sine 50. Okay, so the next thing, if I was just to show you guys again. So the next one is we have the weight going down. So if we were to find the perpendicular one again, this side, we know this is 50. So there are two components we can get. There's the perpendicular one and this one in the X, but we're interested in only this. So this will come out as the weight, which is 400. And then this is cos now, the two adjacent, the angle in the side. So this is cos 50. And lastly, the force which is at the far end. So for that force, it is going down, vertically down. But again, we want to find the one perpendicular. So it is this one. So just as we saw for this, the angle here is 50. So it is going to end up as 2000 cos 50. So now that we've seen how all the forces come up, now the next thing is we have to sum the torques. So all we're looking at is the sum of the turning effects must equate to 0. So if we look at our system, if we go back to our diagram, we should observe that this torque is going in this direction. I can use a different color for this. So we observe that this torque is rotating the object clockwise. So we're picking this point as the pivot. So if we pick this point as the pivot, then these two forces no longer have an influence on rotation, since again, forces acting to the pivot have no rotational effect. So if we look at this force on the other hand is going in this direction. So its influence is anti-clockwise. Then this force at the far end, the influence is to rotate the system in this direction. So we see that we have two forces rotating the system clockwise and one force rotating the system anti-clockwise. So you can take anti-clockwise to be positive and clockwise to be negative. So now the next thing, the distances. The weight is at the center, so it's L over 2. And then the tension we are looking for, it's acting through 3/4 of the whole length, so it's 3 over 4L. And then the third force, the 2000 Newton, it's acting at the far end of the object, of the beam. So because of that, it is acting at the full length L. So in calculating for torque, so we recall, torque is force times distance. So for each object, what we're looking at is, for the weight, we have 400 So remember the component is cos 50. So the length is L over 2. So this, remember, anti-clockwise, it's clockwise. So we say negative for clockwise. Minus, and then we have the other clockwise force at the far end, 2000 cos 50. The length, just L. And then now the only anti-clockwise force, which is T. And then now the ratio we're using here is sine. And then the dimension, the distance, it's 3L over 2. This should sum up to 0. Now, we can move everything else to the negative terms to the right-hand side of the equation. What we're going to end up with is T. And then the next thing that we have is, that's T sine 50. L over 4 is equal to, and then this is 800. Sorry, this is not 800, this is 400 cos 50. This is L over 2 plus 2000 cos 50 L over, this is just L. Okay, now at this point, we can start simplifying this. I don't want to get rid of this denominator. I can cross multiply so that the 4 goes up. This then will become 3 T L sine 50. So all I'm doing here now is just simplifying this really. So there are many ways that you guys can do it. All we're just trying to do is simplify. You can practically finish it from here. So if the 4 multiplies here, it will divide with the 2, remain with 2, and then 2 by 400, this becomes 800 cos 50. So we still have the L. Remember, I'm going to include the L here. So this is plus, the 4 now comes here. This is 4 multiplying the 2000, so it becomes 8000. And then this is cos 50. So you still have the L here as well. So you can divide throughout by L. The L cancel out since it is present on each term. So remain with 3T sine 50. So this is 800 cos 50. This is 8000 cos 50. The 2 can add. So you have 8800 cos 50. So from here now, divide both sides by 3 sine 50. Remain with T is equal to 8800 cos 50 over 3 sine 50. So this now you can work out on the calculator. So if you did that, the answer you get is going to be 2461 newtons. Or you can write this as 2460 newtons. Okay, so this is basically what you had to do to work out this. The second part of the question was asking for, if we just go back to the question, the second part now they're saying, and the forces exerted on the beam by the pin at P. So to get the forces exerted on the beam by the pin at P, so all we have to look at is at that point. So at this point, there are 2 forces. We have this force going this side, and then we have another force going up. So now to account, since these forces, we can take this is the force in the X, and then this is the force in the Y. To get the force exerted on the beam, all we have to do is this force, you can say the R, this force R squared. is equal to x squared plus y squared. So all we have to do is find first what this force, the upward force is. And to get the upward force, we have to go back to our diagram. Look at it. So what we have is this. And then all we're going to ask now is, what are the forces acting in the y? So in the y, if you recall, we have this same force we've labeled y going up, and then we have the weight going down 400, and then we also have this object, the 2000 Newton force going down. These are the three forces which are acting in the y-axis. So now when we sum the forces in the y to say they should equate to 0, this implies that we have y going up positive minus 400 going down negative, then 2000 going down negative. It should give us 0, implying that the force in the y we're looking for gives us 2400 newtons. So from here then, to find the force F acting on the beam, so since we say this is F squared is equals to x squared plus y squared by Pythagoras theorem. So F is equals to the square root of, we found what x was. Did we show what x was? Okay, we did not show what x was. So we can show what x is in the y-axis, because x is this one. And then here we also had this force, which we found, the 2460. These are the only two forces in the x. So if we sum the forces in the x, these equate to 0. So this implies that x is the same as this force. So I hope you guys are able to see that clearly. So that is 2460 squared plus, in the y we have 2400 also squared. So if we work this one out, we get the total for x as 3440 newtons. Okay, so this is basically how you work it out. So this gives us the force. If you wanted to get the angle, of course, how to get the angle, what you have to look at is the angle is just tan inverse of the force in y over the force in x. Of course, this is elementary from the vector series. So if you want to check that one out again, you can always check the link in the description. This just specifies the direction in which this force is acting. We're saying F is going in this direction. So if you want to find the direction in which, by getting the angle, what you're going to get is this theta, which is just the if you by use of tan, it's opposite over adjacent. So opposite is y, adjacent is x. That's how we get the direction. Okay, so I think that's all we're going to do for this series. For the next question, we're going to look at something a little bit interesting now, something about a human being. So this is going to be in our next tutorial. So we have a few things that we want to find. We want to find the force required to just topple a man. So we're given the length of this person, 1.5 meters. Not really the length, not really the height necessarily, but it's the height up to where the force is being applied. The force is supposed to topple the person. Okay, now the radius is given, we're supposed to take is about 0.1. So ideally, we're trying to look at if this is the person. The weight tends, the center of mass is somewhere there. And then now we're saying you're pushing this person from some height up to that point. This is the force that you're applying. And then we're picking the pivot to be somewhere here, since the person tends to rotate in this direction. So this is what we're saying. Now, since the weight is acting downwards, so we're saying, let's take this to be the radius. So the radius, we're taking it to be 0.1 meters. So this is in the first case, in the first scenario. What is the force that we're going to need to topple this person over. So this try to picture it like this. So yeah, that's how we're going to work out the first one. Now the next part is saying explain why the stability of the person against toppling force is increased by spreading the legs. So this is elementary from high school. The two factors which increase the stability of the person, there is the center position of the center of mass, and yeah, let me not say the other one. I'll ask you guys to try it. So I'll try to work out these questions. And then the third one now is to perform a calculation. So saying the person spreads their feet 9 meters apart. So if you're going to spread your feet so that one is somewhere here, and then the other one somewhere there, and then the distance between them is 0.9 meters. So you should be able to see what the radius is in this case, and then try to work out the same problem now and see what you find. Okay, so I'll leave you guys with this question. Try it out. We're going to work it out in the next video. So hope you guys found this helpful. If you did, leave a like. Then if you haven't subscribed yet, make this the video you subscribe to the channel. Otherwise, we'll see you in the next tutorial. This was your tutor.